and we will start from our first team. And by the way, we'll try to make this webinar more like a discussion. We call it town hall meeting. So if you have any question, any comments, feel free to raise your hand and ask, and we hope to make it more of an engaging event today. So the first team is KU Leuven. I guess Xiaobing is here. I'll enable sharing here.
Okay. Hello.
Hi.
I'm Xiaobing Shen from KU Leuven. I will present our work today, and this is my colleague, Qingcheng Shen. Qingcheng Sui, and he helps with us with the structure of the software and stuff. And also I'm with Professor Wilma, who is also here. Wilma, can you hear me?
Yes.
Okay. Then let's start with our work. It's Friday, so I will keep it tight and let you know our work in the least time. And first, I would like to thanks for this chance to have this event to share and exchange ideas about the Corlos model, which is really complex and not unsolved. And for us, our story starts with a traditional DNA network for the iron loss prediction. What we do is that first we use the really traditional, we choose one of the structure of DNA and with a back propagation algorithms and with multiple input. And we use also techniques like use Huber laws and different learning rate scheduler to do the prediction, and it's quite correct, and the prediction is aligned with the target value pretty well. But as Professor Chen mentioned, our research should be fun, that we need to be crazy and think ideas. Then we started to think that all of this data we trained is in a data set we give. And we don't know, such as Corlos operations, it have a lot of operation points and temperature conditions. This can differentiate our Corlos. So we all think, the whole possible data we didn't provide. We provide some range of them. Then we started to think that, what about the other scenarios? That can the artificial intelligence help us, that give us limited data that we can predict as much as we can for the whole possible data range, like outside of the frequency, outside the different flux density, or even outside of the temperature, but keep them in a normal operation conditions. Can we predict them all?
Yeah.
So we do.
Yeah, because like we would like to think that AI's most critical capability is not interpolation but extrapolations. Extrapolation show us the generality of the AI model. But if we're only able to behave really good within the data range, we would think, yeah, it performed really good. But what if, like, what we really want the AI model to acquire is this comprehension of the physical model's capability. So what will it look like outside of the data range that we train our data set model?
Yeah, the traditional one is really good on the training data for sure. Then we do the extra experiment that we select data outside of the training range. It's kind of like straight away. So we think, maybe again, generative adversarial network may help, because it generate and they compare the generation and learn more patterns inside the input data and the output data. So for this feature, and I think we think, maybe it will work on the unseen data beyond the training. So we start our story from the traditional to here so far. Then we started to consider, what is GANnet? Normally in computer science they call it GAN, but to separate our semiconductor GAN, we use GANnet in this case. So we use GANnet for GAN in computer science. So normal GAN contains a generator and a discriminator. You can imagine them as two players. One is to create a fake data to the discriminator, and discriminator to distinguish, your data is real or not real. So it's like a gambler. It's like two players. They are fight to each other.
Mm-hmm.
It's like a loop. And I tell you, discriminator tell you this is fake, and then you improve and predict more accurate. And this is a trade-off, a fight.
Mm-hmm. Yeah.
Then there is a problem. Is that for traditional GAN, like if you didn't add anything into the discriminator, only use your predict or true targets in the discriminator, it only focus on to create that this image is real or not. They don't care these input features. Like I just create an image. You tell me this is real or not. They don't care about your original input.
Mm-hmm.
This what we generator will learn how to generate a realistic image, but they will ignore the input conditions. Okay. Then we introduce conditional GANnets, and what it improves is that for the discriminator, we also input the real condition, your real input, to compare with your output, and it see that you also consider your input, such as if predict the text is red eyes, you have red eyes, it's right.
Mm-hmm.
And even your image is real, but it's not red eyes, it's also 0. And also you have your input, but the image is created, it's also 0. So the only one is considering they will consider the input as well. Then to transfer this to our specification, we use real input data, like flux density, maximum flux density of waveform shapes, and frequency and temperature as input feature. And for generator, we use noise. We use a noise injection architecture. Then for the discriminator, we integrated our real input and our real predictions to do the discrimination. Based on that, we also take related techniques like Huber laws and the special activation functions, and also schedule a different learning rate based on different behaviors, and and try different neural network layers and neurons, the structures. Now we have the results. For example, out of the repack for this is magnetic challenge. So we try it first with the in the middle term. We try some materials. This is one of the material. The first one is use the traditional neural network for the extra text data, and the second figure is that the training process of GAN. Then we use extra tested data that none of them in the traditional data is beyond the training data. So it's also aligns well. So this is also a validation of our structure. And to make it more general, we take MagNet website data to confirm that if this is valuable for it is valid for different materials, different data points, and the left one, the left figure is that we use different materials to train again to see that the training data, the prediction and the real one, they align well, and we use extra text data also from the same source to see that it can predict the
Predict well.
the iron loss really well.
Yes.
Thank you. Then, indeed, still we need to respect this is a challenge, but we don't. We also checked all the test data in the train. It's also in the range of the training data, and we don't know that if you provide more extra data, it is still lines well. But this is our results for the final one, and still, the story is not ending, like you said. Challenge, and we still need to improve it to make it more valid and more perfect. So for our discussion is that from our work we found that even fewer data, this one, the N47 from MagNet website, we find that even within like 300 items is already good enough to predict beyond the training data. And because the parallel processing of these two networks, generator and discriminator, it's really fast. And also future we need to the one we need to consider is to downsize the training error. So now we because of the time limitation along with other work in our team, we don't have a lot of time to downsize the core, but we already did it. So after the submission, so we use log scale on the core loss. Maybe
Yeah, I will carry on. I was participating in this program a rather late stage, and after that we found out that we have really big problem of not able to keep decreasing the errors. Like after training, it becomes like 20% relative loss. So we began to question ourselves, like what is the thing what is the hurdle here? So like when we look at the core loss and our prediction, actually I have prepared a 3D illustration here. So this is a usual figure that we show. Here we can show this is x0 and here is the x1, which is the density, flux density, and also the frequency. And the y-axis, the z-axis is iron loss. Most of them correlates really well, which means like these coordinates really stick with the original one, the true ones. So we were like, this looks good, but when we take it to the log scale, we discovered that the most data point was lying actually down below like 100K. But what we see here, 100K is just a small fraction in the z-axis. So we found out that the prediction difference of 1,000, maybe that's the prediction error, the computational error, right? I mean, it has a difference for core loss prediction, and it has different significance for maybe core loss originally 5,000 or 5 millions. But which means this noise is not Gaussians. Like it has different significance and different distributions on the true data. And if we have something like a relative error that is caused by the computations, and it may pose more severe problem for those who has already a very small core loss. And that's why we will also to think that that's why you are using, the organizer is using relative loss because it's more reasonable to assess the accuracy, but we don't think it's very good for training. A more suitable way to do the training is to do a nonlinear transformation of the prediction of the core loss into a more linear space so that the noise can be more linear, which means the MSE correlates with the Gaussian noise. So this is like a probabilistic estimation 101. When your noise model correlates with your estimation model estimators, that's where your estimator works for the best, right? So after that's why we are proposing like we should use a log scale for the core loss because it has really really uneven distribution for the prediction. Yes, and errors can naturally arise from quantizations and noise of GAN because we're using GANs, but it is the price to pay for the generalization and extrapolations in our scheme. And yes, thank you. This is all I have to say.
Yeah, I think to conclude is that I think we explore the extra text data beyond the training, and this is quite useful because as we know that a lot of materials we have limited data to predict like outside of the range. So, but the story is still going, like you said, and we can update later if we have more good, better results.
Okay, Professor Chen.
Thank you.
Yeah, that's great. Thanks for the presentation. Yesterday from CO Boulder, we saw the random forest model, and today from you guys, we saw the generative advisory network. This is a great exploration because there are just a lot of more advanced tools from the computer science community they are developing, and it's nice to borrow it here. Regarding the extrapolation and generalization, my personal philosophy is that if the model has never seen the data, then the chance of it being able to predict is very low because we don't know what the next material is going to behave. The material may be an interesting material which is very different from existing material, and there's no way the model can be able to predict what's happening. However, if the model, for example, if the model has seen some similar materials before, or it can learn from other material, and now there's a new material coming in, it can make the best reasonable guess based on what it has already seen from other material. There's a chance that it can do extrapolation. And the other thing which I find very exciting about this generative advisory network is you may use it to bound the model, like because we only have limited data, and one limitation of a neural network based approach is that you don't know what's going to happen if there's an unexpected situation coming. And if you can use your generative advisory network to make the neural network safer, like it has seen all the crazy interesting cases and won't be too bad.
Data enhancement. Yes, data enhancement, I guess.
Right. That could be very useful. Yeah, could be very useful. And also the generative advisory network can be used as a simulation tool as well. You can probably use it to mimic the behavior of a material. So these are all great try. And as I said, we'll keep the competition is gone, but the pursuit of the best model is still ongoing. So you are very encouraged to improve the results, and we'll try to set up a server so that if you have a new model, you can upload and then immediately get I think Haoran already have it. So you can basically throw your model, upload your model, and get the evaluation immediately, and we can keep updating it. That's my comments. Very good.
Thank you.
Yep. Any comments from the audience? Any comments from the audience?
Jerry.
Okay, I'll stop sharing.
Haran, Shukai, and Tom, I saw you today. Yeah, maybe Tom.
I have a quick comment. I think your model would probably work even better as we give you more materials, as your material sees more varieties, because I think, yes, the fundamental, perhaps the problem with it is the data you are given versus the extrapolation the performance you can get, because it's based on the data you're given. So I think if you are able to branch out to perhaps nanocrystalline and all these other materials where your base data set is able to see all the varieties, I think that will work even better beyond the MagNet challenge, which I think it's probably one of the most important thrust your work is going to contribute, which I think is very unique from other teams. So I think that's very good.
Yes.
Thank you. I think this is also a good
Yeah.
suggestion. We would like to try that.
Yeah, for now we are just training them separately. Like
Yes.
yeah, we are sure to try them on. Yeah, and also another question, like there is noise that is fundamentally live in the GANs, because in the generator part you need to have noise in order to generate the data. But this also gives uncertainty of our models, which means like when it predicts, the accuracy may not be very good, but the tendency and the extrapolation skills of the model can be amazing. Like we are surprised by how much it can extrapolate. But we need to work on the accuracy issues.
Yeah, sure. Yeah. Yeah, I do have a response to your comment on the noise and Gaussian distribution and things like that. So in this challenge, we don't have enough time, but fundamentally, this should be tied with the measurement noise. So go back to the basic philosophy. It doesn't make sense to build a model which is more accurate than your measurement. So ultimately, your modeling accuracy is bounded by the measurement accuracy. And the core loss measurement at low flux density, low loss, and high flux density, high loss, and low frequency and high frequency, the distribution across the entire operating range is non-even, and it's not Gaussian, the noise. So I would say there are a lot of rooms maybe for our community to really dive into the noise. Like if everyone start to build your own data acquisition system, then we can have a deeper understanding for the noise. And then you should map your noise with the measurement noise. That's the more
nonlinear,
I would say fundamental approach.
Can I do the last comment? Actually, we use our own data as well.
We have our own.
We have we get a lot of size of the ferrous N87 and a lot of size of nanocrystalline. Actually, based on within these two materials, it's really good. That different size we give all the data and use the GAN to do the extrapolate.
The question is, you need to understand your measurement noise at all the different range, and that's very difficult.
Yeah.
Yes, we understand that.
Right.
Thank you for the suggestion.
Yeah. So usually, if you go to very low core loss, it's very hard to maintain high accuracy because you're measuring very small number, and the error is non-Gaussian. We know that. So that's something remaining. I guess community work. It can be solved by one research team. But anyway, this is a great. This is a great direction to explore.
Thanks.
Any other question, comments? No. Okay. So if there's no other comments, we'll move on to the second team, University of Sydney from Australia.